morning, everyone. Today I'll be talking about working on the Android optimizing compiler. Not so much compiler internals itself, but aimed more at getting new members, new engineers up to speed, and hopefully upstreaming patches as soon as possible. I'm Scott Wakeling. I joined ARM last summer. I work in Cambridge, UK, and I'm a Linaro assignee with the rest of my team. So I want to cover today how we work in Cambridge, the Android runtime team itself, tips and tricks for working on analysing performance and debugging work on the compiler, and hopefully to invite discussion as well. So if you're existing members from other teams, perhaps you see something you like that we do or something you think we could do better, then I'd like to hear from you after the talk. I'll cover static and dynamic analysis, testing and debugging, and also benchmarking. We have a relatively new micro-benchmark framework, so I'll give some details about that as well as details about how we do private review, and then how patches are reviewed upstream. So the Linaro Android runtime team grew out of the 64-bit port of Android at ARM itself. We're a subset of LMG. There's currently 7 engineers based at ARM in Cambridge, of which I'm the only Brit, and two new members joining us from Spreadtrum in China. So we're just starting to ramp up with how we work distributed. You're not a Brit, you're Scottish. What do we do? Mostly we contribute to the Android open source project master branch. This is where the next version of Android is developed in the open. We call it TIP. Within the optimizing compiler itself, we work in the back end, obviously. We're empowering ARM on Android, right? So the parts of the compiler that work with intermediate representation and generate ARM and ARM64 assembly. We also do some R&D. There's a reasonable amount of low-hanging fruit in the compiler and in ART right now, but it's slowly disappearing. So we're also looking ahead at what optimizations we might do in the future. Recently, we've looked at prefetch and caching optimizations, SIMD vectorization, and also considering ARM64 simulation on foreign architectures. We also perform member-only optimizations, which we apply to the stable tree, so current versions of Marshmallow at the time we're recording. So what have we done so far? The ARM64 port of the compiler itself, including the JNI compiler, programmatic assembler, VXL, various VM and runtime improvements. Intrinsics, we've been catching up on, doing quite a few of those. They've been very good first tasks for new members. They're a very good introduction to working on the compiler, and it's a good way to get your first patch upstreamed. Our recent members have done just that. A fair amount of instruction simplification. So, for example, recognizing certain patterns of intermediate representation. Bit field rotations most recently. Sometimes we introduce new IR, so not entirely back-end. We do have influence in further up in the compiler. Instruction scheduling is a large chunk of recent work we've done with some significant gains, and various other platform-specific optimizations. How we work, IRC is fundamental to how we work. Especially now, we're starting to work in a more distributed way with people around the globe. Having written communication is easier for some people. Email, of course, video conferencing is something we've used a fair bit in the past. We have this weekly art class, which when I joined ARM, I was quite worried when it arrived in my calendar. I thought that we'd be getting our paintbrushes out, but yeah, it wasn't so bad. We do some good talks, actually. We present slides on what we've worked on. There's a lot of knowledge share, so new engineers, if they can conference in by video, they get to learn something about what we've been doing. Sometimes we just cover general compiler theory if one of us has been learning some new ground. We do private review, so in Linaro's Gerrit and Jenkins, we work there to make sure patches are very good quality before we upstream them. And public review happens upstream. Google do that. So we like to have things as good as possible before we upstream them. First patch can take some time for new members, but typically you could hope to upstream within maybe a month of joining, depending on the patch. Okay, so let's pretend you've joined and you're working and you want to do some analysis of your first patch. So static analysis. Let's look at some IR. Dex2.oat, that's the compiler. That's compiling Dex bytecode to an oat file, which is compiled. It's an ELF file with compiled code in. So we can dump a control flow graph of our Java input. And this helps us look at, for each method, for each pass in the compiler, we can look at each basic block, we can look at the intermediate representation in there, and also the disassembly for that. Now this is really useful, for example, if you're working on intrinsics or instruction simplification, you can look at a before and after view of the IR for that pass. Two tools that I'd recommend new members have a look at for this, because the control flow graphs themselves can be very verbose. They're just text files, but they're not really readable. IR Hydra and C1 Visualizer. So here's an example of what you might use C1 Visualizer for. This is an example of bit field rotations that were done recently. So the shift right ORed with a shift left by the register size minus the shift size. This is a bit field rotation. And what I was working on with this patch is recognizing that pattern of IR and replacing it with a new IR for rotating. Because the rotate right instruction would be a lot more performant than doing your unsigned shift right, your sub, your shift left, and your OR. So on the left, you can see this is before the instruction simplification pass ran with my patch applied. And you can see from 17 down to 20, we've got these 4 IR nodes. Now each one of those may or may not compile to single instructions, but generally less IR means less output code, right? And then on the right side, you can see what the IR looks like after the pass is run. And you can see that we've simplified those 4 instructions down to one single rotate right IR node. So this is a really good tool for looking at how your patch is affecting the IR. Make sure it's doing the right thing. Another form of static analysis is looking at the assembly that's generated itself, the generated code. So you can use oat dump for this. Foo.oat being the output of Dex2.oat, so we've compiled some Java to an oat file. And we're going to redirect the output to a dump file. So boot.oat is a very good candidate for looking at how your patch has affected other things other than your sample Java program. You want to know, have you affected the size of boot.oat? Have you affected something within boot.oat that you didn't intend to? Boot.oat contains the core Java libraries and Android frameworks, so there's an awful lot of Java in there that your patch could affect. However, if you do oat dump boot.oat, you're going to have about 1.35 gig of output. So how do we effectively look for changes in there? We want to see what we've changed. I would recommend two tools, split oat dump. There are links to these tools at the end. So that will take so first of all, if we use oat dump to dump boot.oat from before and after, so without our patch applied and with our patch applied, split oat dump breaks that dump file into many tiny ones per method. And then I like to use meld to compare the two. So you can't read the text, don't worry about that, but every entry in this before on the left and after on the right is a method in boot.oat. So all of your Android frameworks, your core libraries, this is an example of what's changed in Bouncy Castle crypto classes. This is expected. I know that there are a lot of bit field rotation patterns in Bouncy Castle code, and that's really what I was hoping to optimize. So all of the methods in blue have changed, and then I can use meld to go into each one and look. And what's great about this is, on the right, I'm going to see highlighted in blue where there are changes. So I can quickly scan through the whole of boot.oat and see if actually my patch has impacted code elsewhere that I didn't expect, and go and look at exactly what changed. So if I go in to look at the differences in a method, I can see before on the left, the generated assembly, move S and logical shift left, sub and logical shift right and an OR. That's what a bit field rotate looked like before. And I can see after in boot.oat, I've actually just got this R sub and rotate right instruction, which is great. So, dynamic analysis. How can we look at the performance of our patches? We're probably all used to using perf in various circumstances, and you can use that too on your Android device. There's some simple example of instructions here of compiling a class file to DEX and running it on your device, capturing some perf information. I think Android will be moving to simple perf, but it will be just as usable. Hardware performance counters as well. So there's an example there of statting out info about data cache load misses, data cache loads, done during some recent prefetch investigations. So perf is very useful, as always. Have to mention Streamline, though. As low-hanging fruit in art and the compiler disappears, we're going to need to spend more time analyzing what's worth our effort. What potential gains could there be from certain optimizations? Streamline's great for this. You can analyze multiple performance counters at once, perform process and task tracing, and the timeline view is particularly useful. I'll show you some screenshots. Actually working out when within a processor's lifetime certain counters peaked or certain performance problems appeared is very useful. Perf just kind of gives you, like a final summary of the whole of a processor's lifetime. For a particular process, you can look at what functions took what time, and then there's a call path view as well, which breaks down what parts of a function took what time of a processor's life. And annotations too, which is a really useful extension actually if you want to catch particular events during your processor's execution and then see where they appeared on the timeline in relation, for example, to your particular performance counters spiking. Running a capture session on your device with Streamline. Very straightforward. These days, Streamline 5.23 comes with a pre-built Gator-D binary. You used to have to compile it as part of the kernel tree. Push that on your device and do some port forwarding, and then it's very, very simple from within Streamline to run a capture of your process. So by default, the timeline view, which I'll show you in a moment, has a default list of pre-configured performance counters. So you can see some general cache performance counters, branch mispredicts, for example, faults and interrupts, and I/O and memory performance. But you can configure which counters are gathered during your capture as well. There are processor-specific captures available. Processor-specific counters available. For example, you might pick Cortex A53, 57, and look specifically for L1, L2 cache access and so on. So it can be really, really very fine-grained. There's as much information there as you could need if you spend the time with the tool. So this is the timeline view. This is a recent investigation into prefetch performance. So each row is a collection or one performance counter in a particular area. And the highlighted parts of the graph are my process running on the device. So I've selected to look at my single process that I'm interested in running on my device. And these are the counters for the specific point in time that I've chosen. I can see instructions executed by that point, clock cycles. Most interesting here are the three that I've picked for cache information. So I was particularly interested in line refills, data line refills at that point. So I could see actually how many cache line refills had happened by that point in the process. Quick example of the functional, the call graph view. This is a C example. This is useful as we go forward. We're going to need to spend more time working out what is worth our optimization efforts. So we want to know what potential gains there could be from a particular optimization before trying to work on the compiler itself. We might find with a simple example that it's really not going to be worth our time at this point. There might be better work that we could be doing. So you can see 25% of this function's time was spent in the for header, but most of it is the allocation into the buffer. And then we can look at the disassembly, and that gets broken down further. So the 16 counters above samples are broken down further, and you can actually see at the instruction level where the time is being spent. Okay, testing. So your patch is developed, and you've got some good gains from it. How do we test it's doing what you think it's doing, and has it broken anything else? We have some automation now. It's reached the point now where it's really useful. So this is Linaro CI. We've got Jenkins running, automated tests. It's good practice to run tests locally yourself if possible. It saves time pushing it up to Gerrit and triggering builds only to find out that you've broken something that you could have identified before pushing. So we have host tests you can run on your host development machine, and target tests, which you run on devices themselves. G tests, which is Google tests, and IR checker tests, which I'll talk a bit more about soon. They check that IR has been transformed correctly, and benchmarking as well, because you want to test that you have indeed got a significant gain and hopefully not regressed any other benchmarks. The nature of working on TIP is that it's always changing and it's often broken. It's not a finished product, it's in development by definition. I think as I sit there with my patch ready to send up for review, there's around 1.5 billion Android devices in the world. Measure twice, cut once, run as many tests as possible. So to run target tests yourself, some very straightforward commands to run the different tests yourself locally. They can take some time, but it's definitely worth doing before going to internal review. Here's an example of an intermediate representation test. So going back to our bit field rotate example, I wanted to have a test in place that made sure when the Java you see at the bottom, this method called rotate right, that when that was compiled, before the instruction simplifier pass was run, there was IR for unsigned shift right, sub, shift left, and OR. So that's the top block. You can see these check DAG, check directed acyclic graph lines. So that makes sure that when that Java's compiled, before that pass runs, this is what the IR graph looked like. And then the second block in red is what I expect the IR to look like after that pass is run. I want to see only a rotate right IR node. So this protects not just the output of the compiler, but also it catches breaks to actual IR transformation. Someone could commit a patch later in the instruction simplifier that broke this. And actually having this single test fail takes us right to the problem. And when I say someone else, it's always you, right? You break something, and you want to know exactly what you've broken. So having broken something, let's debug it. GDB works, as always, on your target device. There are two options for you. I think on the stable branch, AArch64, Linux, Android, GDB is in pre-built. So that's very straightforward. This run test script that I'm running here is saying run this test over GDB, 64-bit, and this is my test, 557, my art test. Port forward and run GDB. Straightforward. On tip, that binary is not in pre-built anymore, or at the moment. But there's GDB client, which essentially replaces it. It's a wrapper script. So do take the time to get GDB working with your device, because stepping through your generated code as well, you know, what I was saying about 1.5 billion Android devices. I like stepping through code before I push it for review. Something that can help you with this is your compiled oat methods, so all your Java methods that are compiled to what we call art methods. Stepping through those, you don't have a line number and a source file to give GDB, right? Because we've compiled Java to assembly, so we don't have a source file. So how can we effectively stop when we enter a compiled method? If you go into the code generator, in generate frame entry, and insert a break, then GDB will stop as it enters each oat method, which, you know, for a simple Java program can be really quick and easy. It's probably the second break to get into your test method and step through the generated assembly. So, red light, green light. Anyone familiar with test-driven development? They'll be familiar with this concept. I often forget it, and soon after joining ARM, actually, one of my first patches, in fact, I got a green light straight away from the tests, and I thought, that's great. I've written my first patch perfectly. It's going to be upstreamed, it's going to be merged with no comments, and everything's going to be great. But as I thought about it more, I thought, this can't be possible. I've only just got here. So I'll step through the code, and I'll get a red light first. You know, I'll purposefully break my patch just to make sure that then when I fix it, I get a green light again. So I purposefully broke my patch and you know, inserted a break statement in the assembly. And I still got a green light. So what I thought was happening obviously wasn't happening. And like I said, tip is in development by definition. You can't trust that everything else is working. And what I found was that the inliner pass that was running before the intrinsics pass was removing all the intrinsics. It was clearing all the intrinsic flags on all the methods. And so my intrinsic wasn't even running. When I used oat dump to look at the generated assembly, it all looked great, but it wasn't running at runtime. So this is where stepping through code and purposefully breaking your patch to get a red light and then fixing it to get a green one is well worth your time. So we broke something, we fixed it. Let's benchmark it. Both private review and Upstream will like to know what benefit your patch gives. And for added confidence, some evidence that you haven't caused regressions elsewhere. It's all very well uploading something that, you know, speeds up bit field rotates, but if we're breaking something else, we're slowing something else down significantly, then we don't want that upstream. We've started integrating our benchmarking framework into Jenkins, into the Linaro CI. We're already getting reports of all benchmarks by email, differentials to see what's gone quicker, what's gone slower with your patch applied, 32 and 64-bit comparisons. So you can get this information by pushing your patch now to Gerrit. You can also run these benchmarks locally, either on your host development box or on the target itself. It runs on the command line. There's no boot to GUI required. I've run them on a Juno. It's very stable for benchmarking. That link will give you an example of some of the automated reports and graphing that we've already got. It's really awesome where it is at the moment, actually. And we're going to be making it even better. Well, the Linaro automation team will be making it even better with our support. So we can look at the performance test framework itself can also tell us peak memory usage of the dex-to-oat compiler. Oat file size, for example, if we're making things bigger, smaller. We've recently added caffeine mark and benchmarks game suites. So we have around 60 benchmarks now, all with multiple profile points. So we've already got hundreds of points of analysis. There's a link there at the bottom, get access, write benchmarks. So I wrote some slides for the last Connect. We had a hackathon on the benchmarks. People were really helpful. They turned up and helped us write some benchmarks to get the framework going. So that link would be your guide to where to get the framework from, how to contribute. We're adding benchmarks quite routinely now as we write our patches. So we write a patch, and if there's no benchmark to cover that specific piece of work, then we write one. All right, we're getting close. So private review. What does a good patch look like in Gerrit for private review? It hopefully does one thing as per the commit message. It passes tests with one caveat, relative to current head on tip. Tip is in development. I keep saying it, but it's often broken. So with your tests, if you're running them locally, if you don't cause any more breaks than what's currently failing on tip, then you're good for private review. You know, if there's 6 failing tests on the baseline, don't worry about fixing them. Have a look at them. I mean, it might be something obvious. It might even be something that you broke with your last patch. But relative to current head, I would love to know that you've recompiled boot.oat, all of the frameworks, because there's an awful lot of Java in there that your patch can affect. And that you've rebooted your phone successfully. That you've improved something and regressed nothing, so that possibly that's a new benchmark you've uploaded to the benchmarks repo, or at least in your commit in Gerrit, in your patch set in Gerrit, you might quote some benchmark stats for me and say, this is the gain I've got, and I can't see any other significant regressions. We're not Upstream, we're Linaro, but we will point out deviations from the Android coding style guidelines. We'll point out anything that we know Upstream are going to pick up on, because when patches go upstream, we want them to be as good as possible. Once you're through your first patch, you tend to know, line length, white space, they're big culprits. It's not things you typically expect to be pulled up in review, but it will happen upstream, so we point it out. Also, unless you've marked your patch set work in progress or request for comment, please only upload for review if you do believe it's ready for upstream. Upstream review will add some other considerations. They will be concerned with impact on other platforms of your patch. Any clear deviations from existing code. That includes code that you think is not written right or not laid out correctly. If it's a clear deviation, then you'll be picked up on it. Debug checks and unreachable macros, very useful for testing assumptions and shoulds. This should never happen. This should always be the case. I think most of my patches I've upstreamed have had comments about adding one or both of those. So have a look at how those macros work and see where you can use them yourself. Insufficient test coverage is often picked up. If there's no ART test or IR checker test that specifically covers your patch, you could be asked to add one. And once you've upstreamed for review, that ongoing review upstream should be your priority. If someone takes the time upstream to stop by and review your patch, then first of all, you're more likely to get a swift reply again if you respond in a timely manner. It's polite, but also you could save yourself some rebasing. So keep on top of it once it's upstreamed. Okay, in the future, what might new members to our team expect to work on? There's much general compiler work. It's relatively immature, the optimizing compiler. Code generation work, caching optimizations are something that proof of concept work has shown there are potential gains for, definite potential gains, particularly with future architectures. There's a simulator which is ongoing. Sim devectorization is a possibility. Something else, something that you want to work on, something you've identified as important, that you'd like support of the team to work on. The one caveat there being that, of course, everything does require upstream appetite on tip. Upstream need to want it. Stable is ours, but you can't guarantee everything will be upstreamed. So some resources. For all new members, the Art New Starter section on the Linaro wiki is your first port of call. We have worked to make that better and better. As each new team member has arrived, we've improved it. That was certainly a lifesaver for me when I joined. There's the LMG reference library, which has really useful information about, for example, using perf on Android that I mentioned earlier, using GDB to debug on the device. The Linaro Google Drive has all of our art class slides, all of our weekly art class slides, lots of information, slides about the benchmarks repo, how to write benchmarks, lots of useful information there, and it's always being added to as well. Android code style guidelines you should get familiar with, and DS5 performance analysis tutorial, so using Streamline, will become increasingly important as we move into more non-trivial optimizations. And the split oat dump tool which never cleared review, but I find it really useful, so I should probably update a patch for that and see if we can't get it merged. Okay, so that's all I've got. Do we have any questions? There's one.
I'll ask the first questions.
Okay.
Is there any other presentation on art today?
Yes, Sherban, I would have hoped you would remember that you have a presentation almost straight after this one. Sherban will be talking after me. This is the first of 2 talks really aimed at new members. Sherban will be talking about the infrastructure that we're building within Linaro, as well as some other topics about working on art that I haven't covered. So do come along to that. It's called Art 2. Is it in this room? Yes. Yep. Okay. Yep.
Hello, my name is Xue Liang. I'm a very new member of this art team. So I have 2 questions. The first one is, you mentioned that you are the British in this team. So I would like to know that the variety or the diversity of your team members. If there is an engineer who does not speak English very well, or speak English as their first language, how will you help him to do good communication to someone like you, or someone to do good communication with someone in Linaro in the United States? My second question is that you mentioned that your team have done very great work in art testing and benchmarking. So if I am a validation engineer, I like to do validation. Can I just join and just focus on all the art testing and benchmarking tasks? I want to learn from you guys on how you do testing and benchmarking, and take those all your great work on art validation back to our home company and help improve the quality and help the test validation of our products in our own home company. Thank you.
Okay. What was the first question? Okay. First question. Right, let me mentally walk around our room in Cambridge. So I'm English. One of my colleagues is Scottish, Romanian, Bulgarian, French, Russian, yeah, Chinese, yes. So that's the breakdown. We have just gone global with our two new members from Spreadtrum, and we want to get better at what we do, how we work with people around the globe who don't have English as their second language especially. Right now we feel that IRC as written communication is a very good way for us to all communicate effectively. It stays on screen. There are plugins for translation. We've been using it when we arrive in the morning in Cambridge and people are just going home in China. We get to catch up on IRC. I think we could also do our weekly art classes. We could have people coming in on IRC. So it's something we want to improve on. I think written communication is probably the best way for us to work as a team. Video is possible, but it might be difficult, I understand. Does that answer the first one? Yep, okay. Second question. Can people work, if they want to, exclusively on benchmarking and testing and validation? Yes, absolutely, absolutely. We have a planned backlog of work to do on the compiler in Jira. We use Jira and Kanban process to manage that work. But essentially, new members can bring with them what they want to work on. We may advise about upstream appetite and so on, if we even know, you know. But testing and validation and benchmarking, yes, certainly. And with regards to sharing how we analyze performance, yeah, there's no reason not to share anything we know about within a Linaro context, what we know about architectures, using Streamline, how the benchmark framework works, and how we track performance, and what we use those figures for, and what goals we have. Does that answer that question? Yep, okay. Anybody else? Any other questions? No one's going to ask me about SIMD.
I'll ask you about SIMD.
Where's that? Oh. Okay, so we're done then. Okay, thank you very much. Thank you.